Okay. Thank you and welcome everyone. Welcome to this lecture of the Italian chapter of SMC. So just a few words about our chapter and our initiatives. As you probably know, the System and Cybernetics Societies is one of the society of the IEEE that has more than 4,500 members, with 7 journals and magazines and a lot of activities we will see in a moment. The focus of our society is all about humans. So we put the human at the center of our activities. In particular, we focus on human-centered research and development with 3 areas: system science and engineering, human machine systems, and cybernetics. And as always, the membership of this society, as happens also for other society of the IEEE, gives you the access to several benefits, in particular the possibility to read and stay updated about novelty in this field via journals and magazines and the digital library, a lot of events and conferences. You will receive also discount for registering to the conferences organized by this society. And the membership is quite cheap. It's just about $12 if you, of course, already have the membership of the IEEE society. So I said SMC organizes a lot of conferences and events. In particular, the flagship conference is the System and Cybernetics Conference, which is always organized in the beautiful venues. This year will be in Malaysia at the Borneo Convention Center in October. And we are also organizing, as the chapter of the SMC, the Italian chapter, we are organizing several special sessions. As soon as this special session will be accepted, we will inform you. And so please submit your paper before the deadline. Another initiative that we have organized as the Italian chapter of SMC is a special session at the conference on automation, science and engineering that will be held at the end of August in Bari, in Italy. In particular, we have organized a session on safe and secure human-machine interaction. During this session, as happened also last year in a different conference, we will also celebrate the Italian SMC Day. So please consider to submit a paper to this special session and to join us. There is still time to submit a paper before March 15, okay? Last thing, we have also sponsored a conference, the International Conference on Critical Information Infrastructures Security, that will be held in Rome at Rome Tre University in September. And also in this case, there is still time to submit a paper before the April 15. Okay, so now we can move to our lecture series. This is the second lectures of this year. Here you can see the schedule also of the next lectures. Usually we will organize a lecture at the end of each month, the last Friday of each month. And today we have the pleasure to have here Professor Marek Reformat from the University of Alberta in Canada. He will give a talk on weighted common sense knowledge graphs, construction and utilizations. Just a very brief introduction. Professor Reformat is a full professor at the Department of Electrical and Computer Engineering at the University of Alberta. His main research interest is about developing new methods and techniques for intelligent data modeling and analysis, in particular using some computational intelligence techniques, in particular fuzzy computing and possibility theory, as elements for capturing the relationships between data and knowledge, and again to mimic human reasoning, which is a very important topic also for our society. He's also an associate editor of several international journals, the organizer of several conferences related to computational intelligence and also to software engineering. He was also the past president of the North American Fast Information Processing Society. He also organized several conferences regarding FATSI, like UseFlat and so on. So, Marek, thank you very much for your presence here today, and the floor is yours.
Okay, thank you very much. Let me share the screen. Giuseppe, let me just maybe start officially then.
Okay.
Everything okay? I think
it
looks like I have a red screen. So, Giuseppe, thank you, and everyone, thank you very much for giving me a chance to give a presentation about some of the work which was done with, as a matter of fact, with one of my PhD students. And I'm glad to kind of say that it is around the human in the center, or human as a main kind of maybe not center of the computation, but kind of looking at the human, how the human learns about the world. And in this particular case, we were looking at the common sense knowledge. And because one of the things which are quite interesting is in ontologies and the knowledge representation. So in this case, the topic is about building or constructing and utilizing up to some degree the weighted common sense knowledge graphs. So it's all about the common knowledge which usually we take as human for granted, but in the case of the intelligent as well as potentially autonomous systems, an awareness of the surroundings, knowing what's going on in a kind of common sense level seems to be of potential interest. So I will start with a few words regarding the motivation of that work. So Jan LeCun is one of the big names, if we can say, in AI. For him, according to his definition, the common sense is a collection of world models representing what is likely, plausible, or impossible. So anything which is around us and give us as a human ability to move around, to do different things, which, as I mentioned earlier, we take for granted, but at the same time, we learn through most of our life, starting being infants through the kids and so on. So of course, our common sense knowledge grows, but at the same time, we do it through most of the time. So as I kind of mentioned earlier, it looks like to have eventually intelligent system, mostly from the point of view of and kind of robots and awareness what's going on around, as well as the autonomous ones, this ability to recognize what is happening, not maybe on the factual level when we have the knowledge about maybe countries, maybe people, but knowledge about what is around us, what is on the table, what we do regarding the sitting in the chair and walking and just avoiding different obstacles. So as I kind of mentioned, the aspect which we try to kind of look and kind of also justify when we look at the common sense knowledge is the fact that we are gaining that information from multiple different experiences. So in general, it's experienced through the fact that we walk, we also touch things. We have also, maybe I will just do it in this way, also visual stimulus, which is probably one of the first ones which we deal with as a human right after birth. We also have the verbal input, which also talks about, okay, please don't do it this, fire is usually dangerous, cold, don't touch it. That type of information which give us, again, common sense knowledge about the world. Many of the things which are related with the common sense knowledge are also context dependent. So depending on in which contextual environment we are, that also involves different versions or different importance of some of the things which we learn. And of course, as in the real world, we cannot do things without looking at uncertainty and the fact that not everything is just black and white. And that's another story which comes also from my research, meaning that everything is fuzzy. There is no yes and no, many things and many degrees of values, if I can say, between false and true. And it also associated with the fact that we just learn, and of course, more we learn and more we are all through the visual input or through the verbal, through the context, through the interaction, we eventually, with time, decrease this uncertainty, but it is there from the beginning and up to some degree stays with us. So having that, maybe a little bit of a big statement, but it looks like the common sense knowledge is really the knowledge about the real world. And that's kind of what the topic is about. And in this particular case, the idea which you will see, which we try to kind of first come up with and then realize, is the aspect how we can build that common sense knowledge. But before we do that, I have to mention a few words about the representation which we used here. And in this particular case, this is form of the graph, which is called the knowledge graph. It is one of the kind of byproducts of the whole movement in the case of the building intelligence on the web, which is called the semantic web. So the principle or the atomic part of the knowledge graph is very simple. It's just something which we call the triple, which in this particular case represents the basic piece of information, which really is kind of a links or relation between two entities. And in this particular case, the entities and the relation have usually names, which is subject, property, and object. And we see some of the example of the very simple triples, which at the same time kind of are a little bit close to the human way of looking at this, because they are very simple statements. Like John has a car, John will be subject, car will be object, and then there's relation between these two entities, meaning that John has a car. The graph, the knowledge graph, is the directional graph, so that means that we have eventually the origin, if I can say, of that statement or that relation, and eventually the relation goes from the subject to the object. Once we have that set of triples, meaning set of basic information blocks, it's just a natural to think about this as a graph. And that four examples of very simple triples are kind of shown here as a graphical graph-based representation. And as you can see, the nodes represent the different entities and the edges represent relation between them. And of course, it's relatively large, if I can say, or freedom, how some of the things could be represented. Of course, there is multiple different constraints. Eventually, what could be a relation, what could be a subject or object, but excuse me, but in general, we talk about something which is vocabulary, which in most cases, if we have the knowledge graph, we follow that because we want eventually maybe the graphs to join or to merge or to be eventually translated from one another. So the language which is used to express the relation and the entities is important. But in general, as you can imagine, if I add some things about John, maybe where he lives, or maybe about the profession of a teacher, or maybe what type of car it has, that graph will grow and grow. So in general, it's not also a concept which is kind of only academia. This concept of knowledge graph shows up quite a while and for quite a while and in multiple different places. Many of the companies we suspect have that knowledge graph behind. Not everything is available as for the public domain because it involves some efforts to build, and it contains what is most interesting is semantic information. So example of that would be, I have few examples. It kind of looks appealing from the visual perspective. This is a snapshot or just a super subgraph of information about Edmonton. So in this particular case, we have a dot here in the middle, which represents the entity Edmonton, and then every of the dot that kind of in a zoom in represent any other piece of information. Could be Could be people, could be organizations who have headquarters in Edmonton. I think that there is some information about the NHL team. All the connections here, we don't have labels because that would be kind of difficult to read what is behind, but each of the nodes, as well as each of the lines representing edge, has the label, meaning has the type of a relation, as well as what is the nodes, what they represent. So that's kind of example. Another example could be maybe a little bit zoom in. Here would be indication that we have multiple different flavors of music and how they're connected, probably singers and groups, all of that somehow related to each other. And whenever it's relation, that's something appears as a potential form or way to represent it as a graph. So as you can imagine, the fact that I introduced that kind of concept, or represented to you the concept of knowledge graph, is because we want to represent the common sense knowledge as in the form of the graph. And that's kind of is all about. But just for a little bit of a fun, I ask DALI, so it means that it's a GTP language model to generate the knowledge graph about Italy. So that's kind of what it come up with a little bit of a tuning here and there. That's what ChatGTP thinks from the point of the knowledge graph as a representation of Italy. You can see that it's not perfect. Some of the concepts appear multiple times, but that's kind of, if we would say to the language model, okay, just do it, and it will create the knowledge graph. It is not so simple task. I'm not saying that it's a super difficult. It is a little bit of a challenge to kind of make it a way that it kind of makes sense and it's really valuable. So common sense in the sense of the information which we deal with is different than factual one, because the example here would be if we have the plate with some dessert on it and utensils on the side, we take it for granted that fork and knife and spoon, what is on the plate, that plate is on the table, there is a tablecloth. We don't have to kind of worry about it at that stage. But when we are kids, when we are younger, we have to also learn all that things. But we learn it through experience, through visual stimulus, through the verbal stimulus. So what we really would want it to do, we want to really to build automatically that information which represents some of the real world scenarios, but and represent it as a graph. So of course, again, just for the fun, I ask GTP to create a graph about components, objects, elements in the classroom. I keep the classroom because there is also example down the road about the classroom. So that was kind of what was generated by the ChatGPT. It took me a few minutes to tweak a little bit what the components I kind of wanted and how it would kind of look like. And that, on the other hand, is for the room in the restaurant. These two topics I kind of put that because I have examples of that for these two environments also regarding the reasoning, because we use eventually that graph which we created regarding the world information or the real world information as an example down the road. So that kind of is beyond us when the language model help, or at least tries to do something about it. And you know, even naming and all that thing is kind of, but it was very quick, just a place, give me an image. So what is, as I kind of already mentioned, the idea is the solution is we will use the common or real world items as a nodes in our graph. So just the idea is relatively simple. We have all the things which we've seen around us as a nodes in the graph, and the relation between them as a relation edges in the graph. So in this case, if something is on the table, something is besides the shelf, or it's on the shelf, that the flower is in the vase, this is all relations which we were interested in, because this is something which describes our environment. One of the things which also wanted not be realistic, but we also wanted to have flexibility in potentially expressing what we want to put in a graph, as well as heterogeneity of the sources. As kind of the process comes that we as human learn from multiple different media, different sources of information, we wanted to do this also ability to, when we build the graph, that we can use multiple pieces of information coming from different places, and an easy expansion. As you can imagine, if I have just another triple, for example, coming back to the information about the car, if I know that, okay, the car is of a type Fiat, I will just add that information, and automatically it will kind of click to the graph, and the graph will grow without too much of effort. So that's also is one of the attractiveness of the graph. So to come up, we wanted to have different sources of information. We also wanted to do the contextualization. So in this case, you will see that when we eventually start building it, we also not only look at the, for example, the laptop in the classroom, but maybe what about the laptop in a restaurant, or maybe laptop in the office, or laptop in the park, something along this line. So we wanted to see also what environment is for specific objects and how things change. We wanted to do also the weighted relations. So that means that, again, coming from that aspect that the fuzziness and some of the work with uncertainty is associated with the fact that not everything is kind of a clear cut, we wanted to be also able to say that if there is some relation between objects, that this relation is strong or weak, or it's valuable, or it's kind of a true to a degree. So in this particular case, our knowledge graph not only has the label associated with representing what is the relation between two entities, but also we associate with that the weight, which represents the importance or strength of the relation between entities. And we wanted eventually to do some reasoning once we have that all and contextualization as well as the weighted relations. You will see we use some elements from the possibility theory to do a little bit of a simple, in this particular a little bit of a toy type relation that we can combine context, weights, and reasoning to some interesting. Hopefully you will see that in a moment, some interesting procedures or applications of that graph. So I will talk a little bit about how we really did the construction of the graph and how we utilize it. So finally, the outline of the presentation. Sorry for that. So idea is simple. Because of the new technologies, and probably some of the things is already a little bit outdated, so we would probably do it a little bit of different tools right now. But the idea is, as the human first perceived the issue through the visual stimulus, we look at the images. So the idea was we analyze images, multiple images, we fuse information extracted from that images, and through the fact that we see multiple images and repetition of items and relations, because we analyze each of the image individually, we eventually add all of these weights to connections to identify, based on the frequentionistic approach, how frequently they occurred in the set of images which we processed. So we look at the pure deep kind of learning type of a tools, which allows us to analyze the image and identify objects on the image and the relation between them, and generating something which is called the scene graphs. So it's not this part we kind of look at what is happening, because that was interesting for us, what we can obtain in the case of the common sense knowledge from the images. So example of that kind of a scene graph is here. You see the picture of the person probably feeding, yes, it's feeding a horse. And through the process of analysis, identification of the objects on the images, and also through the learning process about what type of relations could exist between this, we could obtain a graph like that, which is called a scene graph, which have the objects identified on the image as nodes, and relation between objects as edges or relation between them. So for example, men wearing glasses, so it was men recognized as an object, glasses were recognized as an object, man was holding a bucket, yes, horse eating from the bucket, man feeding horse. So that is, and of course, as you can imagine, even that process is getting better and better, but the idea is we automatically, through the visual stimulus, obtain information about what entities, of course, depending what type of images we deal with, are on the images and what are the relations between them. And we built that. So the process is such that we have in total, when we started, we had 30,000 images coming from a data set. Each of the image was processed through that tool, which allows us to generate the scene graph. So you see that from each of the image, we obtain the scene graph. And then what we did, because the identification was relatively abstract, meaning it was just a person, maybe man, maybe woman, maybe car, but without too many details, what type and things like that, we could relatively easy fuse all of these graphs. So the idea was such that we generate multiple graphs, each graph from a single picture. And then once we have so many graphs, we fuse them in the sense that whenever the object was about the man or the car or some kind of animal or horse, everything was put together. So in these, all the nodes which represent men were kind of glued together as a one node man, but then we have a multiple relations to a multiple different objects, which in many cases the man will deal with. Of course, the information which we extracted and eventually embedded in the graph, maybe embedded is not a good word because the embedding is a little bit of a different process, but which we have in the graph, of course, depends on the images which we use. So in our case, we use images representing a variety of things regarding scenarios in the household, as well as things about different parts, like you will see that we use, for example, things what is on the table in the multiple different contexts. So once we have multiple scene graphs, we all aggregate them and created something which we call the world perceiving knowledge graph. So we apply the deep learning network, identify objects, detect the relation between them, and then creating scene graph and fuse them. So we use 30,000 images from the visual genome database. We process them through the tools, which up to some degree we also tweak and make sure that they give us reasonable results. Of course, they were not perfect, but there's also interesting story behind that. They don't have to be perfect because of the fact that multiple images are processed. We kind of through the fact that the same scenarios appear on multiple different images when we fuse them, some of the things which were maybe wrongly identified or treated as a noise will appear very infrequently in the graph. And when we look at the weights and we try to eventually see the importance of the relations through the multiple occurrences of the same triple, the triples which appear maybe once or twice because of some problem with the scene graph generation were kind of not automatic, but kind of naturally become very, very unimportant or become very little importance. So we have that, when we fuse that, and we also have a multiple different ways how we determine the weights, depending on the views. Sometimes we use the information from these models because they get the probabilities of occurrence of specific relations, and we combine it with the frequency of occurrence. So eventually, I cannot show you because it was too large, but if I even take a part of that and kind of try to show it, it is multiple different elements here, and all of them are kind of very much connected. So it's not the easiest kind of image to see, but if I just we take very small snapshot with the plate in the middle, we see that there's multiple different aspects which shows up with a different type of relations. So during a training, we started with a specific number of relations. I think it was 50 different relations which we can identify. I think that, I don't want to exaggerate, about 300 different objects. So you see that, for example, on the plate, it could be a handle on the plate, banana, fork, woman is handing and man is holding a plate. It could be on the plate, off the plate food. Pizza is on the plate and table. So now we see also directionality of the relations. That plate is on the table and there's a cup on the plate. So that's kind of information was eventually processed automatically and we obtain. I mentioned that there is a weights. So that means that if we take another snapshot, and in this particular is the vase, and we have a flower, counter, table, plant, and window, there's also kind of in a form representing different relations. So the vase sometimes is in the flower, probably should be opposite, but as I mentioned, you see also as a kind of a labels in this case for the relations, even if the relation is really kind of represented a little bit in different form, the frequency of occurrence of that. So you see that maybe appeared in that particular snapshot or subset of images just twice. 31 times it appeared that the vase has a flower, that the vase is in the counter, that the vase is has a plant or is with the plant. So we started with this frequency of occurrence because that was automatically when we fused the information, we just kind of counted how many times a given triple appeared. And then we used different techniques to identify, in this case, the weights, which we wanted to have between 0 and 1. And we have different approaches to do it, to make also sure that something which we built has kind of a human validation process, so it's kind of the truth up to some degree or close to the reality. We used the Amazon Turk. We used the process in which we prepared multiple versions of the triples, and we ask people kind of outside, so we outsourced that process. And eventually, depending on the different techniques which we have, we also look at the consensus between individuals who have evaluated. There was not a super large group, but eventually one of these things, accuracy 95% regarding what people will perceive as because we asked kind of to a degree, because we kind of translated, we had to prepare the data for the evaluation. So that was kind of done. The next thing which we wanted, okay, where is the contextual information coming from? So then we analyze images in a specific context, and then we generate against the scene graph. But now we labeled, because we have that information, we labeled images with information about where the image was taken from. So in this case, we labeled the information about the context. Would that image was taken in the kitchen? Would that image was taken in the classroom? Would that image was taken in the park? That information we knew by the labeling, so the kind of a classification on other case, different images. Once we have the classes of images, we perform that process again, and we obtain, I don't know if I can zoom in right now, but this is a snapshot. That was even more convoluted in the case of the graph. That was snapshot of that graph. Here in the middle, you see the plate. So that we're saying, okay, plate in the multiple different scenarios. And we see it was even pictures, table in the car, table in the bathroom, table on the ship, table in the woods, table in a restaurant, table in a party. So we had table because of the contextual information. We know where the table was taken picture of. So was it really in a restaurant? Was it really in a classroom? Was it in a park? We also look and, of course, identify what elements are on the table. And you see, it's kind of a little bit of a more kind of a gray out, but through the colors as well as the thickness of the lines, we had all the weights. So in other words, the kind of interesting story was that, okay, if I had for example, plate, and we have a table in a restaurant versus the plate in the table, maybe what would be a kind of example, maybe in a car, maybe a small table in a car, definitely the stronger connection was to have a plate on a table in the restaurant than the plate on the table in the car. So the idea was such that the contextual information in this particular case was represented as a strength of the relation between entities. So that's kind of would be zoom in just to another example. In this particular case, we look at the cup. So we look at the cup, and this is where we also start to look at the process of reasoning. So, but let me explain that figure in a moment, because it gives right away some motivation and also the understanding what we really did with the reasoning. So if we have a cup, we have three environments: restaurant, classroom, and the bar. So this is the three, for example, classes of the images which we have, we process, we build that graph. You see that, for example, in the case of the cup in the restaurant show up 696 times. So when we have pictures of the restaurant, among so many, close to 700 pictures had the cup. So the pictures from the restaurant had the cup on it. Among them, close to 100 were cup on the table in the restaurant. In another environment, which we had the classroom, the cup appeared only 36 times. And in the classroom on the table appeared among them the 36 5 times. In the case of the bar, cup appeared on 287 pictures taken in the bar. Among them, 50 of these pictures had a cup on the table. So that gave us a lot of information about contextual kind of awareness, meaning that, okay, even looking at that, seems that the cup is much more frequently appeared in the restaurant and in the restaurant on the table versus in the classroom and kind of in a bar between. So that idea and that information gave us the idea that we could do the reasoning from the point of view that if we want to know where the table is based on the fact that the cup is on the table, we could do some simple reasoning and identify the location of the table. So we saying that, meaning that we did this. So we use some elements of the possibility theory. In this particular case, we look at the conditional aspects of the possibility theory. This is just a few equations which indicates that once we have the information about one element in a conditional to another object, and we have probability of existing of one of these objects in the environment, then we can identify what is the probability in this particular P and Q. And what is really interesting in this case, that we don't look at the one value, but we look at the interval. So that means that in this particular case, when we look at the process of reasoning, what we obtain is not just the one value, but the range of values, which indicates that when we have evaluation process or when we do the reasoning, we obtain the lower and upper bound of possible location of possible probability, well, in this case, it's possibility, it's not probability, it's possibility of this particular item. And we follow some of the math. It's relatively simple, and eventually we put a problem in front of us which we wanted to solve, meaning there is a few items on the table, and based on these items, can we identify where the table is located? So what we took is a bunch of few elements. In the case of what we did, so the P part from this possibility theory is just a set, in this case, of elements which you can find on the table. So in one, because we have three examples or three scenarios, what you can see on the table. One is the A version, which is paper, bottle, book, laptop, and cup. All of them you see on the table. And the question is, okay, if you see all of these 5 elements on the table, where the table is? Is it in the park? Is it in a restaurant? Is it in a classroom? And then we had the version B, which is just a paper, book, and a laptop, or just a bottle and cup. And through a very simple the thing which we obtain from the graph, we identify where the table is depending on our assumption what the items are on the table. And it could be, we just took into consideration three possible locations: a bar, classroom, and restaurant. So when we just took a very small snapshot of that graph just regarding this, and we have this right now on the table, through the process of reasoning, we obtained the following values depending on what we started as an initial probability that really we see. So we can also include the fact that we could be uncertain about what is on the table. So in this particular case, we were certain that these items are on the table. In this scenario, we were not very certain. I would say that we were quite uncertain what is on the paper, on the table. So in each of the cases, the restaurant identified as the narrow. So the upper bound in the case was from the possibility reads look like, okay, if we see something that it's possible, but what was interesting is really the necessity part, the lower bound, and in this case the higher is the value. Of course, that means that it's a more possible that location of the table is in one of these environments. So in both cases, when we are certain what is on the table and we are not very much on the center of the table, we obtain the same results that when we see these 5 elements, it's quite likely that we are in a restaurant. It could be things that because of the laptop and book, we could see things in the classroom, but it seems that the other one, and also the fact that, yes, again, through the experience, through the number of images which are related to the restaurant versus bar versus classroom, we see that majority of information which we had is restaurant. So that means that the evidence coming from the restaurant, because it was experience of our knowledge graph during a training process, was very much kind of skewed in this case towards the restaurant. But that was because of the exposure, having ability to have more images from restaurant than for other places. So it's really what we wanted to kind of also show and explain, that it also depends on your individual experience. If you as a human are more exposed to one type of environment, you will know better that environment than the other one. And that kind of also is shown here. So that was with the 5 elements on the table. When we have just paper, book, and laptop, that right away, it is still quite high in the case of the restaurant, but dropping the bottle and cup pushed the classroom pretty high, even if the classroom was exposed very little in the case of during the training process. We just had 36 examples of a cup in the classroom, and only among that 5 on the table. That is just the cup. So we should also look at the book, the paper, the laptop, and the bottle. Yes, the other 2, some notes in the. So maybe I should mention that of course this is just highlighting one element, cup, but of course we had also information. So as you can imagine, the paper, book, and laptop was much more often appeared in the classroom than in the restaurant. And the last one was just the bottle and cup, and that diminished quite a bit the classroom and the restaurant, but push up the bar. Not very high, so it was not super conclusive, if you can say, but among these 3, this seems to be the most likely location of our table. So that's example of the utilization of the graph for the reasoning purposes when we ask the questions something related to the contextual information. The language models show up in the meantime. So we said, okay, we started with the visual flow of the information. We processed the images. We got the scene graphs. Can we do something with the language models from the point of view of the next stimulus, which we human experience, meaning the verbal one? So in this case, we added 2 things kind of at the same time. we equipped our graph with the linguistic terms, because in this case we wanted not only to identify the weight, but we wanted kind of get more information about the likelihood or how likely or unlikely are some relations, and we wanted to use linguistic terms for that. And we also used the language model to expand. So the example here is such that once we have our original model, we pick one triple, we prompt in a specific way, we build the prompt automatically based on that triple, and we ask the language model to extend and to give us more information which could relate it to a different aspects of that triple. Could be related to the subject, means the window, could be related to the building. So you see this very, very simple example that if we take the window is on the building, when we prompt that to the language model, we obtain more information about where the window could be, and also what could be also on the building. So you see in this particular case, we kept the same relation. You will see a variation of that in a moment, but in general, we take something from the existing graph, which we started with the visual representation and processing. We prepared automatically a few questions to the language model, and the language model gave us results. We filtered that. So of course, the things which we already knew, we just confirm and increase the strength of the relation which we have already in the graph. But the things which were new, we added. So we have not looked at the aspect. So because we were multiple times different questions, so we also had eventually the aspect of the frequency occurrence. So we did different prompts. We used a very simple prompt in which we can just extend it some kind of example, what you just have seen, or the subject or object. We also have a new relation. So in this case, the user can identify, okay, I'm interested in some other relations. Like maybe I will go in the circle, because that would probably, because this one is the most appealing and sophisticated one, if I can say. We also look at the fuzziness of that. So you see I hope that you will see, I apologize for the size. Most likely in this particular case, we just look at the aspect of the strength and kind of represented in a linguistic form. We prepared the prompts, and again, we obtained the results. You see that at that time we had the access to GTP3. We built this whole process automated to generate automatically prompts depending on what type of extension we would like to use. Very simple one with the fuzziness, or with a new relation. So in this case, we could come up with a new relations. The new relations were also associated with the fuzziness in the case of the linguistic terms representing the degree. And again, a very short, it was like a one shot, two shot training process, and we obtained quite interesting results also from the point of view of extending the graph through the interaction with the model. We also did human evaluation. We used the Amazon mTurk to do that. Again, prepared the results, obtain this in a form so humans, which we have no idea who they were able to determine the quality of the triples. So we had the simple triples generated from the language models, fuzzy triples, and fuzzy triples with the user relations. It was not perfect, but it was in the range of 70% among different number of triples which we provided for the evaluation, that the correctness was at least encouraging to do something more. So with that, when we so far paused the thing, so we kind of build eventually the word perceiving knowledge graph, and we wanted to kind of show the methodology. The tools could change, but the process would kind of stay the same. We start with the real world knowledge from the point of view of images which we process. We generate the scene graphs out of that, and we fuse them. Then in the next stage, we also look at the aspect of extending that through automated process of interacting with the language model to fuse or introduce a new information which maybe is not always possible through just analysis of the images, and maybe in some cases just the labeling of some of the things. Yeah, so it was kind of interesting to see that we can start fusing information automatically. What we wanted, and we kind of try to do that many of the things which we deal with, and also with the graph, is also context dependent. So we have not only information about objects, but also environment in which these objects appear. And through the fact that we have eventually the weights, we have information about end occurrences, and eventually building the degrees or include the uncertainty in some connections. We could use the possibility-based reasoning schema and eventually utilize the graph in some form of a querying what is possible, what is more likely regarding, in the case of the contextual information, the context in which some of the items, elements appear. So to kind of have the final conclusion is that the weighted common sense graph with the possibility-based reasoning seems to be, at least in our kind of a humble opinion, some kind of a maybe way to introduce some intelligence into systems, some awareness, some autonomous also, because many systems will work or should work with us. It will be not that they will live in their own world. So that means that they have to also understand our world, and that common sense knowledge seems important from that perspective. And ability to represent it as a graph. It has also one more maybe interesting aspect, because many discussions right now, okay, if you have language models, they contain a lot of information already, why we need the graph. One of the interesting, and I hope important aspect of the graph is the explainability or interpretability. Yes, the explainable AI. Now when we have the graph, we can really see what's going on. Yes, we can kind of go back. We can see why some of the things were done, what connection exists, what the relation is, how strong the connections are. So thank you very much. I hope that I try to be on time, but probably I will went a little bit above. But thank you very much. I hope that you find some of the things at least interesting. Thank you.
Thank you very much. Very, very interesting. So if there are any questions, I have a couple of questions, but if someone has some questions.
Okay, so how I do, okay. I have to go back somehow out of this, but I can still sharing, because if there is some questions, I can go between.
I start with a question suggested also by Graziana. Do you think that this kind of approach can be used, or if you have performed some experiments with images regarding humans performing some specific tasks? So for instance, you have a lot of images of human working with a particular machine or systems, and you would like to observe these in order to predict the behavior of the humans, to make some kind of inference, to check if it's working well or not.
Yes, I think that the thing which is eventually part of the knowledge graph and which information in the knowledge graph very much depends on what images we process. So if it happens that we have images associated with that type of activities, humans in different environments, maybe in a manufacturing line, or maybe even in an elderly house, or any kind of activities which we deal with in our homes, that information will be processed. So it's more maybe this. I hope that approach for building a common sense graph is applicable to any environment, but it very much depends on what type of information we feed into the kind of a pipeline, if I can say. Yes. So if we have images associated with any type of activity, And we have a good tools to process them. So it means to identify the objects on the images, and that's getting better and better. Yes, in the case of what we can identify as a object of interest on the image, as well as training the tools to identify specific relations. So once we have that, that automatically goes to the graph. Yes, so. And if you have multiple of that images, the same issue with the weighted ones, and then all that processes of maybe even more sophisticated and interesting from the point of view of extended through the interaction with the language models, and then eventually building the mechanisms. Because when we did this reasoning, we didn't do it on the whole graph because it's just too much. We just took the subgraph, which was kind of items relevant to the question, and then we process that. So I think that it is possible. I hope that that's more as an interesting, hopefully, methodology, but applications depends very much of what you feed into the system.
Probably in order to do something like that, probably we need also to consider the time dimension. What do you think? The temporal dimension of what happens?
Yes. Because and that's again, if we have, for example, snapshots, like let's say we take the video, because we also were thinking about the video, yes, from that perspective. So we take the video and you do the snapshots, let's say every second or maybe every minute, depending on the dynamics of the activity. Then you can have a time steps associated with the images. Then is the issue how you represent that, because no matter what, from each image you generate the scene graph. Yes, and that if we label that scene graph with the time step, then the process which maybe needs a little bit of more thinking how to do it kind of elegantly is the issue of when you fuse the scene graphs, what do you really do with the time step?
Yeah.
So it could be the case that you have just kind of like a snapshots of the graph, and you have eventually versions of the graph, or it depends how you represent the graph, time in the graph.
Yeah,
because that's. But I think that of course it will make things a little bit more complicated, but I think that it's an interesting idea, and having the time involved and see how some of the progress, because in this case you can do the reasoning not maybe from the point of view of context, but maybe over the time. So if you look at the time t and then the time t plus delta, can you say something between these relations? Yes, it means that the time, so you can transpose the context into a time context, kind of. That would be interesting. Yeah, very interesting. Thank you. Thank you for the question. Yeah, good.
There is a question from Giancarlo.
Yeah, thank you. First of all, thank you very much for your very interesting talk. Pretty, let's say, complementary with respect to our research. Also, the concept of common sense, common sense, I like to say that it's a tough beast in the sense that, according to where you are, common sense could change.
Yes.
I'm also professor, I'm also professor in China in many different universities, and they don't have forks, they got chopsticks. Okay, they don't drink coffee like in Italy, but they drink tea. For example, if you come at my home, I'm bought from Italy and bought from China because I got chopsticks and forks. I got coffee and tea. So this is something that, in my opinion, should be also considered, because sometimes otherwise you can have some kind of distortion with respect to the reality.
Yes.
Okay.
Yes.
And another interesting aspect is related to how common sense changes over time. Okay, because common sense is not always the same. Okay, so
Yes.
apart from these philosophical questions, I'd like to be much more scientific, technological. Okay. So I got two questions. The first one is related whether or not you are using reinforcement learning in order to drive, or to tune better the knowledge graph you are able to produce. Even, the weights, okay? They come from, a data set, a huge data set.
Yes.
But maybe if the humans are in the loop, I mean, you can use some method in order to, let's say, adjust. Okay, so this is just an intuition. I use reinforcement learning in other contexts, not just in this. But I don't know if this could be applied. Okay. The second one is related to, of course, generative AI. Okay, because we are all playing with generative AI. Okay, in different ways, even to create some kind of large language models or even small language models. So I was just thinking about the creation of small language models starting from a data set, your data set, for example, based on images or based on video, okay, without considering the time dimension. Time dimension is another very, very, very tough beast. But anyway, what do you think about, reinforcement learning from one side, and my second question related to small language models?
Because I think that this aspect of adding the reinforcement learning is very interesting, because you can think about some of the ways as maybe associated with some rewards, or maybe as a kind of a policy which you eventually build, yes, through the reinforcement learning, from the point of view of strength of the connections as a potential selection of the actions. Yes, how you would. My experience with the reinforcement learning, at least from it is a little bit of a time-consuming process. Yes, so that means that I have to say that right now one of my students look a little bit different way. So we try to see if we can use the knowledge graph or knowledge graphs representing the environment to speed up the training process on the RL. Here would be to use the RL for. I think that, if some process, how we can think, I think that will be very interesting to see how we can do this, because there is also work which involves the reinforcement learning for identifying the shortest path, or kind of helping a little bit of reasoning, but it's more on the existing graphs. In this particular case, it would be to potentially argument or enhance or improve the graph using the reinforcement learning. I do not know how it would work. It means how it would be, the details, how you can do it, but I think that would be very interesting to apply. And I hope that the performance-wise, it will be also feasible, that it will not kind of collapse because of the complexity. So I think that, but now it's a deep neural reinforcement learning, so probably everything could be pushed into the neural networks. But I think it will be very interesting. I think that I don't know the details how it could be done, but I think that that is very interesting idea. Now, the second part regarding the building and tuning and maybe adapting the language models, would that be even a small one? There is kind of interesting story about, in general, how the language models and knowledge graphs can kind of, could they coexist? Could they benefit from each other? And I think that having, I would see this more like a little bit of like a kind of a loop, meaning that we can maybe start with a simple thing regarding the knowledge graph, maybe as a seed, very simple one, add this different media regarding the images as well as the text, because quite often the knowledge graphs are generated from the text as an input, or as some kind of a involvement using the language models, that they can process some of that text, generate maybe triples, use that for evaluation purposes in a loop and go back. That would be one potential. I've seen also work that they see, okay, because the knowledge graph might be going from this directions at the beginning is such that it could kind of narrow down a little bit the scope, because we know that there is issues with the language models, how they perform, and these are probabilistic machines, so many things are based and they can go kind of wander in the multiple different directions. So having the language, the graphs, which represent some knowledge, to kind of maybe speed up the process of training, because we focus on specific domain, we do not go around. The way around would be that maybe a little bit of things which we tried, maybe in a very simplistic way, how we can prompt the maybe starting with a few elements as a part of the graph, go to the language model, get more information about that particular aspects, objects, relations, add them back to the graph. We can use maybe, there is multiple agent type of language model scenarios that you can use some of them for, because in another work which we dealt with language model, we use language model also for some kind of evaluation purposes. So it kind of gives some indication what kind of is correct, what is not. So I think that in general, it's the field which is very interesting right now due to the abilities and the tools which we have, how we can kind of do things in a more interesting way, and also better in the case of the product down the road. So I think that the synergetic type of relation between graphs and language models hopefully will give us better results. I don't know the details how it could be done yet. I'm not saying that it will, but we work also around that because we have another work which we use the language models, we tune the language models for one particular task of building graphs, but they're all based on text. So I don't know if that's the answer which you anticipated or you like. It's a little bit of a kind of a little bit kind of like a hand waving. I don't know details.
I mean, let's keep in touch. We can continue offline, hopefully.
That would be great, yes.
I also just would like to give you greetings from Matteo, because we were discussing offline about reinforcement learning, about large language models and so forth. So definitely, let's keep in touch. Thank you very much.
Thank you very much.
Okay.
Thank you for the questions.
There is another question from another friend, Sabrina.